you've kind of seen the basic argument, and then some of the impacts of climate, why we care about it, why we want to learn about it and try and mitigate it. And now I want to just give you a little more depth in the climate science. So what are some of the actual mechanisms that are driving these changes? So the biggest issue is the Earth's energy balance. So essentially, like any system, if you want to keep the system in equilibrium, you need to have the same amount of energy coming in as energy you have going out. If you have more energy coming in than you have going out, then the system warms until it gets back into equilibrium. So that's the very basics of what's happening with global warming with the Earth. So here you can see the basic graph here. So you've got solar energy coming in from the sun. Some of it is reflected by the atmosphere. Some of it is reflected by light surfaces. So ice in particular, things that are white reflect the sunlight. Darker colors absorb it. So the Earth actually absorbs the energy and then re-emits it in a different part of the spectrum. So if you remember, I think in one of the very earliest lectures, Professor Holtman talked about black body radiation. The idea there is that everything that has a temperature emits radiation. So the sun has a very, very high temperature, and it emits radiation in the visible part of the spectrum. That's why we can see the things that the sun lights up. The Earth has a much lower temperature than the sun, clearly, and so it emits radiation in a different part of the spectrum. But that radiation gets emitted, then part of it goes back into space, but part of it is absorbed by greenhouse gases in the atmosphere. So they absorb it, and then they re-emit it back to the Earth. So it kind of bounces back and forth in the Earth, each time some of it getting passed out into space and some of it being refracted. And so when you talk about the greenhouse gas effect, I think one of the interesting things to keep in mind is that's really only an example, obviously, so it's not, but the mechanism is actually a little bit different. So in a greenhouse, you're literally trapping the air, or like a blanket. You're really trapping the air next to you, and that's what's creating warming. In the Earth system, it's actually the energy being reabsorbed and re-emitted, which is a little bit different. So this is the IPCC graph showing climate forcings. And we talked already a lot about different greenhouse gases, but on here you can actually see the magnitude of the effect that they're having. So CO2 is the one that we care about the most, not actually because the molecule is the most effective at trapping heat. There are other ones, so methane, for example, is actually more effective molecule for molecule at trapping heat. And the chlorofluorocarbons or halocarbons are actually hundreds or thousands of times more effective at trapping heat. The thing is, there's a lot less of them in the atmosphere than there is of carbon dioxide. So that's why we care a lot more about that. Water is also more effective at capturing heat than carbon dioxide. And I've heard in the past people say, well, why don't we just focus on H2O? Why are we so worried about this carbon dioxide? That's not even the problem. Well, the problem is we can control carbon dioxide. We can't control how much water is in the atmosphere. So the H2O in the atmosphere really just has to do with the temperature. So it's a feedback, not a forcing. So here's just the list of those greenhouse gases: carbon, methane, the halocarbons. And then you can also see on here the aerosols. So we talked about that a little bit in the initial quiz. Most of the aerosols, the lighter colored aerosols, actually reflect sunlight. And so they lead to cooling on average. And like I mentioned with that, the way the temperature in the past rose, and then kind of flattened a little bit and rose again. So when we had significant pollution and aerosols in the air with that flat period, and when we had clean air programs and started getting rid of some of the aerosols, some of the smog in our cities, then you saw the heat rising again. So it's kind of an unfortunate side effect of clean air. Black carbon, on the other hand, which is the kind of carbon, I believe, from fuels and things, and it's a pretty straightforward name. It's carbon that is, or aerosols that are dark colored, and they actually absorb heat. So unlike the other aerosols, those drive the climate to be warmer. And at the bottom there, you can see solar irradiance. So as always, the solar irradiance does have an effect on the climate. It does have some driving force. but it's much smaller than the anthropogenic or the human-caused changes. So I just mentioned briefly climate feedbacks, and the idea here is that what we just saw was climate forcings. These are things where what you put in actually affects what you put out, and you have control over that, or it's something external that's driving the system. For feedbacks, you really don't have any control over that. It's something that happens naturally. So a couple of the examples you hear about a lot, probably the most common one is ice. And this is one of the reasons we see big changes in the Arctic, is that as the temperature warms, that melts the ice, and then you get less ice coverage and more open water. And the open water is very dark. So instead of being the white reflector that ice is, it absorbs a lot more of the heat, which causes greater warming, greater ice melt, and then continues to have that feedback loop as an amplifying effect, or a positive feedback. Another positive feedback is water vapor. So, like I mentioned before, the temperature in the air is essentially how determines how much water vapor can be in the air. That's why when you're in DC in the summer and it's really hot, the humidity is horrible. But if you're in Minnesota, where I'm from, in the winter, humidity is not a problem. So it really just depends on the temperature of the air. So as the temperature rises, you get more water vapor in the air. That causes more heat to be trapped and re-emitted. So more water vapor can go into the air. So that's another feedback that amplifies the climate warming. A negative feedback would be, as climate warms, you get more water vapor, you get more clouds. And one effect of the clouds is that they're white and they reflect more sunlight. So that aspect of clouds can be a negative feedback. So you're actually causing cooling. So something that you get warming, more clouds, then the clouds reflect it and causes cooling. So negative feedback. But clouds are actually very complicated system. So there's also, for example, the fact that clouds trap more heat and re-emit that back to the ground. So the overall effect of clouds is actually very difficult to accomplish positive and negative feedbacks associated. Okay, so the next thing I want to talk about just briefly is climate models. So when you're going to build a climate model, you basically identify the physical principles of the Earth. So what are the basic equations that we know that govern the way Earth dynamics work? And then they use computers to run simulations that go through those equations and determine what's happening. Complicating those basic physical principles is the feedback, the types of things I just mentioned to you. So it's not an easy input-output for these models. They have to work in these feedbacks and figure out how that actually is going to affect the end result. Another complication, you really can't model the Earth full scale or really in any very small precision. So about what they have now is about 50 kilometer cubes. And within each of those, they just kind of average what the temperature or what the conditions are within that cube. As you can see in the graph, there's the horizontal and vertical, vertical, with, so all 3 dimensions, sorry. And they're looking at the land, the sea, the ice, so they try to, and the atmosphere, so they look at all the different types of processes, all the different types of land cover, particularly in the general circulation models. So these are the most advanced types of models. So one of the problems that happens when you're working with these cubes is that there are effects that are smaller than 50 cubic kilometers. So for example, clouds. Clouds are not generally a kilometer or even close. And so what they have to do in that case is they come up with what's called parameterizations. And they try to think of ways to, for example, clouds, they might average the cloud cover over that whole area. So to represent the idea that maybe one side is cloudy or there's one cloud, we'll just average that over that cube. So the models are really hard to make. There's a lot of things we don't really know. So why do we trust that the models are actually worthwhile? Why do we care what the output of the models is? So one of the things that makes us trust them is that they're able to reproduce regional effects. So for example, you guys are probably familiar with the El Nino effect. It has to do with the oceans warming. It causes different types of temperatures over particularly North America, and a little bit in South America, I believe, also. And so that effect is something that they don't program into the models. They don't tell the models that's supposed to happen, but it does occur in the models. So that makes them believe that the effects that they've put in, the equations that they're basing things on, are complicated enough to reproduce some of the things we see in the actual climate. They're also able to reproduce historic climate conditions. So that's another reason if you start with the climate conditions we know occurred at some point and run it forward, you can actually reproduce what's happened. And even for things like volcanic eruptions, if they put in effects like that to say that that happened, then the model will show that that leads to cooling, which is in fact what you see in reality. So those are the reasons that their ability to recreate these things we know exist is why we trust in their ability to be useful in predicting what's going to happen in the future. One of the things with models when we were predicting the future is it doesn't only matter how good the model is, right? No matter how great of a model or how perfect of a model you create, you still can't tell the future of what humans are going to do, right? So one of the things the climate models do is they come up with these different scenarios of what will emissions be. So how much fuel do we think humans are going to use, how much energy do we think people are going to use, and then they can run the simulations and see what the effects would be. So we've talked about kind of all the science and the mechanisms that are driving climate change, and I gave you that whole argument in the beginning of why this is happening. And that's not to say that there aren't any open questions in climate science. There are a lot of climate scientists thoroughly engaged in research trying to figure out more about it. So I wanted to go through just some of what these questions are, some of what the ongoing research is on, just to give you an idea of what we don't know yet. So the first thing, and probably the most important from a policy standpoint, is tipping points. So we know that tipping points exist. We know that there's some point you drive the climate up to where a little extra change causes a huge change in the climate. So for example, with the younger dryas period that I showed you, there was fairly steady warming, and then at some point, a whole bunch of fresh water went into the ocean, shut down the ocean circulation, and then you had very rapid cooling. Very rapid on a geographic scale, not on a day after tomorrow scale. But still within 10 years, I believe. So we know those tipping points exist. We've seen them in the past climate record. We don't really know exactly at what point they happen. And so that's the kind of one of the biggest concerns right now, and particularly for policy, is we know at some point we'll reach the edge and it'll kind of be too late to stop these catastrophic changes. We don't really know where that edge is. Then some more specific things that people are looking into. One, solar radiance. So we don't have any direct measures of solar radiance prior to 1970s when we started measuring it with satellites. There are some ways that they can try and understand it in the past from measurements on the Earth. But really what we want to do is get a longer measurement of total solar radiance so we can really continue to make that argument that it's not the sun driving climate, that we can really see exactly how the solar radiance changes. Aerosols, dust, smoke, and soot. We have a lot of ideas about how we affect climate. There are things we know, for example, the black carbon increase in warming. Most of the other aerosols decrease warming to some extent. But exactly, they also do things such as the aerosols in the air can be used for water vapor to attach to, essentially, and create more clouds. They stay in the atmosphere for different periods of time, so there's a lot of kind of open questions about exactly what the effect of aerosols is, and that's something that we would like to know in more precision than we do now. So that's something that the error bars are a little bit bigger on. Again, for clouds, like I mentioned earlier, the feedbacks on clouds are not particularly well understood, so there's just so many feedbacks that happen. So increased warming because they absorb heat, decreased warming because they reflect heat. And some of the things they've determined already, it depends. The altitude of the cloud matters. The composition of the cloud matters. So there's a lot of really specific things that change how that happens. So trying to understand the global effect of clouds is very complicated. So that's work's underway. The carbon cycle. So we know that the ocean is removing carbon from the air. We know what percentage it's taking out. But that's changing a little bit, and we don't completely understand that mechanism of how much gets taken out and why and how might that change over time. Also the ocean circulation. So ocean circulation is very difficult to measure, you can imagine. And our global ocean data sets only go back to about the 1990s. So that's another thing that we really want to collect a longer term climate data measurement. Precipitation. So one of the things, I showed you some images of drought in the Southwest, and then I showed you about those trees that had too much precipitation, which caused fungus to grow and killed off this forest. So those precipitation effects and how they differ in different regional areas is a big area of research. So you can imagine, I just went to a hearing on Capitol Hill with NOAA and NASA, and one of the people they had speaking was the head of the Governors Association, State Governors Association. And basically all the state governors are saying, we don't care that much about the global change. I want to know what's going to happen in Nebraska. So that's what they really care about. And that's something that a lot of research is going into right now. And finally, sea level rise. So you guys have maybe heard, but in the IPCC report, the only sea level rise they really took into account was the sea level rise from this thermal expansion. So just the water getting warmer and taking up more space. They really didn't take into account the effect that the Greenland ice sheets or the Antarctic ice sheets might have. And so that's another area where research is really moving forward to try to understand what that impact would be.